Hello. Hello.
Yes.
Hi. So, yeah. So, how are you guys? So, I will start today with discussing couple of problems. Actually, one problem that you kind of told last time. One of you told the mother vertex problem. Okay, and other than that, there was someone pointed out about a doubt in the section 6.7. So that particular section I will not be discussing now, because I think that section will, if I, so the question that was asked there is that it is fine, it is kind of, people can understand without too much difficulty how to, so it is like the sequence matching and all. What is the uh, minimum cost for the sequence matching? That how to solve it using dynamic programming with linear space complexity, that could be fine. But how do you find out the actual sequence matching? That was not fine. That was not clear. And in fact, that's a bit tricky. This is in fact slightly involved. So what I will do is that I will possibly take another class at some point of time, maybe this Friday, Saturday or something like that, and do it. Because I don't want to spend today's day whole class on that particular problem. Also, maybe I can ask one of the TAs to kind of conduct a special session on that particular problem. So I will start with this problem of the mother problem. I will just discuss it for short time and then go into the next topic, which is the kind of where I want to go very quickly. So do you guys remember the mother vertex problem? So you have been given a graph G, which is a directed graph. Oh, sorry. I have not shared my screen. Can you see it? Hello?
Yes, sir.
Yeah.
Yes.
You have the graph G, which is a directed graph. Okay. And the question is that, does there exist a vertex V such that all other vertices are reachable from V? Now, I'm certain, I mean, maybe some of you have got this, or have found this answer or solved this answer. So, but anybody who could have actually found this answer? Hello? Nobody found this answer? So actually there is quite a number of finding of answers that could be done, okay? Some of it close to this one was proposed last time by some students, some friends of yours and all. So I will, this is one option that one can do, okay? This is one attempt that one can do, okay? So let me just call this one attempt, first attempt. Yeah? Yeah, tell. Hello. Hello, somebody told something and this got cut. I mean, am I audible?
Yes, sir.
Yes, sir. You are.
Okay, I'm audible. Okay, so maybe that person has some problems with it. This is first attempt would be to kind of, now this is something I will not do, okay, but you might want to go and find out. So this is the directed graph, right? In a graph, in a normal undirected graph, it is very easy to break it up into connected components, right? Using DFS. How do you do it? Or DFS or BFS, whatever. You start from a vertex, do a DFS. Excellent. Fine. Then you will go and reach all possible reachable vertices, or all the vertices in the connected components of phi. So in an undirected graph, right? If I start from a vertex, I run a tree like this. At the end of the day, I will get all the I will reach all the vertices that are connected from this vertex. This is in the case of undirected, right? And then if I am not done, I can start with another vertex which has not been reached, and I can also keep on running some DFS or BFS, and I will get some more tree, another tree. And by doing so, and the idea is that between these trees, right, there is no edge. So these are components. So this is these are the various components that you can think of, right? And there is no edges between these components, and they becomes the connected components. Fine. What happens in the case of undirected graph? Sorry, in the case of directed graph. In the case of directed graph, so just by saying that, okay, here is a graph, I start from a vertex, and oh, I go all along, and oh, this is the set of all the things that are connected from this vertex. Very good. Okay, this is a vertex. That doesn't. Okay, now what happens if I do another vertex? Say I start with another vertex, the new vertex, maybe I use a different color. And when I do this stuff, I am hitting this vertex back. Okay. Or maybe I don't hit this vertex, I go from here, and then there is a path. There's a path within itself, maybe from here to here, kind of stuff like that. So that means this vertex therefore becomes in the connected, I mean in the set of vertices that are connected from here, from this vertex. So of course, connected components is not a right thing to do, right? In the case of directed graphs, what is the connected component? It's not a partition of edges of the vertices. In an undirected graph, the connected component is a partition of the vertices, but that is not the case in a directed graph. Okay, so what is it that gives you a similar flavor to connected components in a directed graph? Have you guys seen it in your discrete math course or something?
Strongly connected components.
Right. This is a concept of strongly connected components. What are strongly connected components? Strongly connected components, okay, are the ones in which you can go. I mean, it is a class of it. So I can break up my graph into this is a strongly connected component. What does it mean? That every vertex for any two vertices here, there is a path from U to V, and there's a directed path from U to V, and there's a directed path from V to U. Right? And the strongly connected component is a partition of the vertices of a directed graph. I don't remember whether we had discussed this particular problem anytime in this particular course, but I expect you to have done it in your discrete math course. If you have not done, please let me know. Okay, so the strongly connectedness. Okay, so you say that U is strongly connected to V if there exists a path, directed path from U to V and a directed path from V to U. And this relationship is strongly connected, is a equivalence relationship. And hence you can split up the whole vertices into a set of disjoint, into a partition of vertices, right? Now, a natural question to start with is that given a graph, given a directed graph, how to find these strongly connected components? Was this question given in any of the previous assignments or stuffs and all, or problem sets?
No, sir.
No. So this is a problem that you might want to really think of. Okay, again in linear time it can be done. This can be done in linear time. And think of it that if you can solve this particular problem, then using this one, you possibly able to find this solution also. That is one attempt to do. There are quite a number of attempts, okay, that can be made on this particular problem. This attempt I'm not explaining. But instead, let me explain you a much more simple solution to that problem. Okay, so this is the second attempt. The first attempt I'm not doing. I leave it to you guys to think about it, and in the meantime, I'm saying is that think of this problem. Okay, think of this problem. How do you do this? Fine. Second attempt is that let's see. So this is something I think kind of something one of your friends had proposed last time, but I think he could not formalize it very well. I don't remember the name who actually did that. So here is the graph G, right? You start with any vertex and you go and do a DFS from here. Okay, so these are on the directed path. Okay, so at the end of the day, so this is all the set of vertices that is reachable from this vertex U. Okay, fine. Now question. So let this one be the, I will say that the reachable from U. So this set is the R of U. This set is R of U. Means these are the set of vertices that are reachable from U. Okay. I'm not writing this definition exactly. So you guys are following me, right? R of U is the set of vertices that are reachable from U. Of course, that DFS manages to find. Question is that, can R of U contain, no, I made a mistake. So okay, what happens? So of course, if R of U, so this is not a question. Okay? This is a, okay, maybe I'll leave it in the question and then I'll see. Question. Can R of U contain a mother vertex? What do you think?
It cannot, because otherwise R of U would have been the entire set.
Very good point. So see, okay, okay, there's two things. First of all, if R of U is the entire set, okay, so this is the answer I can think of. Okay, first of all, if R of U is the entire set, then U is the mother vertex. We are done, right? But if R of U is a strict subset of the entire set, then if there exists a mother vertex, say V in R of U, what do I know? What do I know? That if there is a V from mother vertex, then for all vertex in G, there exists a path. So all vertex, let me call this one, all vertex W in G. Okay, there is a path from V to, directed path from V to W. That's by definition of a mother vertex. And because V is in R of U, so I know, and because V is in R of U, there is a directed path from U to V, which means that there is a directed path from U to W, which is not possible. A contradiction, which will give you a contradiction, because I have started with this fact. So, okay, so that means I can say that R of U cannot contain a mother vertex. Excellent. Okay, we have made some progress. Okay, good. Now, how much time does it take to kind of run this algorithm, find out all the R of U? If I give you an U and I go and say that go and find out or go and mark out or go and find out all the vertices that are reachable from you, how much time will it take?
Linear time.
Linear time. Can you be a bit more specific?
Order of M.
Order of M.
M.
M. Do you
V
think
plus E.
V plus E? Do you think it will be really take V plus E?
Like in case it actually takes V plus E, we are done.
No, no, we are not done.
Because we would have reached all vertices, right?
Yes, exactly. In case you just have taken V plus E. So let me put it this
We are
way.
just doing a DFS.
Take DFS, BFS doesn't matter, right? So it will take, you're right, it will take linear time, it will take V plus E, but think it a bit more clearly, okay? This is R of U, okay? So the time taken for finding this one is, I claim, to be the size of R of U plus the size of the edge set of R of U. But edge set meaning the induced edge set. Are you guys with me?
Yes.
Yes, sir.
Right? You understand that, right? I mean, nothing, because any edge that is not here, say something like an edge here, that will not be even touched, right? So why will it cause any problem? Even an edge that is coming from here to here, that will also not be touched, because I only have information of things going out. I don't have any information of things coming in, right? So only edges on which my DFS will be working are edges of the form, I mean, edges within R of U, right? And so this is it. This is very crucial to understand it, okay? This is good for our running time, okay? To final running time, good. Okay, good. So now I know that here is an R of U. In this much time, I have managed to find out R of U, and R of U is not the whole vertex set. That means this vertex set does not contain a mother set at this point. Okay. Let me do the next thing. I go to a new vertex and do the same thing. Now I don't do the completely same thing. What do? I continue here. I find out all the edges, all the vertices that goes out here. Of course, there are some edges that are like this, right? But as soon as I go and hit a vertex that is already marked, that has already been in R of U or has been marked as visited, I said, okay, it's marked as visited, let's come back. I don't proceed doing that. Okay, so by doing so, I end up producing another big set of all the vertices that is reached from this vertex. Okay.
So
Yeah.
but now we may not reach U from the mother vertex of this.
No, you might not. This is not a mother vertex or not, I don't know.
Okay, sir.
I'm not even saying any of those things, okay? I'm eliminating things. Now, V is not a mother vertex, right? So I have the R of V. R of V is what? All of them that are reachable from V minus R of U. Okay, or let me like R of V minus R of U, kind of stuff like that. Okay, this is the R of V minus R of U. Right? Now, can this R of V minus R of U contain a mother vertex?
Sir,
Yeah.
so when constructing R of V,
Hmm.
when we reach a point of R of U, we
Yeah.
continue without taking that point. Right?
No, we just think that that vertex is done. There is nothing after that. We think of it in DFS, right? If you
Yeah.
ever visit a vertex which is already marked, which is already finished,
Yeah.
you don't continue that direction, right?
Yeah, but we continue with R of V, right?
Yeah, we continue with R of V.
Okay.
We only think of that this set of vertices are done. So we'll get, oh, it is already marked. Let's go back.
Yes.
Okay. Fine. So this R of V thing. Okay. Now, can this R of V minus R of U contain a mother vertex?
No, sir.
The same argument, exactly same argument, right? If it contains if okay, no, let's say that it doesn't, it is not the whole set, then it doesn't contain a mother vertex, right? Okay, let's say that it doesn't contain the whole set, or meaning R of V plus, I mean, this two, there are some vertices that are still untouched, right? So R of V or union R of U is not the whole set, then it's still, there is no mother vertex in this whole chunk. We are now sure. Okay, fine. And more importantly, how much time did I take to compute this R of V minus R of U?
Total will be mod RV plus H set of mod RV. Sorry, mod of H set of RV.
That is not true. Okay, so it will be first of all the size of the RV minus RU, right? That is the set of vertices in this set. This is the amount of vertices in this set. Plus, I have walked down certain number of edges, right? What all edges have I walked down? Set of edges that I've walked down is, of course, the internal edges here, right? So maybe I should just, I don't know how to do. Okay, so I'm just writing it here, okay, in the side. Okay. So this set of edges which are completely within R of V minus R of U, right? So edges like this. I have walked down that lane, right? And I have walked down lanes of this. Okay. So which is plus E of R V minus RU, meaning this part, cross RU. Meaning edges which are across, I mean, going from edges that are going from this part to this part. Is it clear? Think of DFS. DFS, don't think of it as a black box. Think of DFS. DFS, how much time does it take? It takes the total number of vertices and how many edges on which it has gone down. Right? How many edges it has looked into? Oh, is there is from I am at U? Is V a vertex? Oh, yeah. Is U V a edge? Yes, I go and look along the edge UV and so on and so forth, right? Okay. Yeah. Any questions so far?
No, sir.
No, good. So what means that?
Sir, can you?
Yeah.
Sir, can you please once again tell why U is not the murder vertex? My internet went for a while. Can you please repeat that part?
Oh, okay. So if U is so first of all, if U is a mother vertex, then you would have reached everywhere, right? Every element should be reachable from U.
Yes, sir.
So if R of U is not, so if R of U is the whole set, then of course U is a mother vertex. I get my mother vertex and it go off. Okay. But if R of U is not the mother vertex, it's not the whole set, right? So then maybe let's say that let's just think of it in a different way. Let's say that this vertex is a mother vertex. Can it be? Because if this vertex is something, I know that there is a edge from here to every other vertex, right? So by transitivity from U, there must be an edge to every other vertex. And that simply contradicts the fact that R of U is not the whole set.
Yes, sir. Yes.
Fine, clear?
So Sir, actually, I was asking for V. Actually, I couldn't understand which one was U and which one. I understood U1.
Oh, the V is also same. V is also exactly same. See, if from V, okay, I'm assuming that from V you have not yet reached everywhere. Okay, that means R of V. So this set is not the complete set. This set is strictly smaller than the total element V. Or in other words, there is still some vertices here that is left untouched.
Oh, okay, okay,
Okay, in that case,
okay, okay. No,
I
that
don't have any
is fine.
vertices here, right?
Yes, yes. No, so that it is fine. Yes.
Okay. Okay, so total, so till now, how much time have I spent for doing all of this computation? Till now, the amount of time that I've taken is, of course, this plus this, right? Which is actually, if you just do this calculation properly, it is this set plus the total number of edges induced by this set. Okay. So although I've done linear twice kind of stuff, the total thing is still linear. Okay. If you keep on doing linear many times, then it goes off, right? So that is exactly the reason I looked at R of U and this thing separately, kind of. I mean, I didn't think of it as E plus V, but I looked at it much more in a much more specific way. Okay. So total thing that I've done till now is linear in the total R of V union R of U kind of stuff. Fine. Any questions so far? Hello.
So it's fine.
Okay, good. I have not yet told how to find your mother vertex. Okay. So I will keep on doing it like this. Okay. This is just the first instance that I told you. So I maybe start from another vertex and I looked at all of these edges and I know, okay, there are some edges like this. I don't go here and I have a cutoff and all. Okay. I keep on kind of chipping out things, chipping out blocks and say, oh, this cannot have a mother vertex. So this cannot have a mother vertex and so on. Okay. And note that all I'm trying to kind of convince you is that at any point of time, the total amount of energy that I have spent or time complexity that I have spent is linear in the total of the things that I have left out. Okay, fine. Now consider the final set. Okay, say there is a mother, say I start with this vertex here W and I manage to reach all of them. Okay, now I have completed the whole thing. Okay, fine. But what does it mean? It means that from starting from W, I can reach all the other vertices that was not touched. Okay, there can be edges from here to here or something like that. There can be edges from here to here, but I still don't know whether W is a mother vertex or not. Okay, so more importantly, what can I say? That if the mother vertex exists, it must be in this set. If it exists, I'm not saying it exists. If it exists, it must be in this set.
It must be W if it exists.
Yeah, good. I mean, if you are seeing it, then great. But let me explain. Okay, fine. So if it exists, it must be in this set. Okay. And now let's say it exists, and this is the vertex. This is the mother vertex. Let's call this M. Okay. What does it mean? If M is a mother vertex, that means from M I can reach everywhere. Right? But I know by definition of this last stage that I can reach from W to M. So yeah, M might be a mother vertex, but in that case, W is also a mother vertex. Because I can go from W to M and then go to everywhere else. So if at all the mother vertex exists, if at all a mother vertex exists, this W is one of them. Okay. So what have I done? I've thrown away things which cannot be mother vertex. Finally, I found a vertex which completes the whole thing. Okay. It doesn't mean that I can from looking at this structure, I cannot say that this is a mother vertex or not, by the way. But all I'm saying is that if mother vertex exists, if a mother vertex does exist, then W is a possibility. Not a possibility. If a mother vertex exists, then W is a mother vertex. Okay. And now what do we do?
Perform full DFS taking W as source.
Exactly. Confirm a full DFS starting W as source. If that reaches everywhere, then you have got it. Okay. So basically, you keep on removing sets of vertices that cannot be mother vertices till a time comes when my only one vertex is a candidate mother vertex. It is still not clear that that is the mother vertex. But the candidate mother vertex, I have only one. And if a mother vertex exists, then this has to be it. Okay. Maybe there are other mother vertex. That is not a question. But if any mother vertex exists, then this is a mother vertex. So you start and do a DFS from that vertex, and you get it. So is this clear?
Yes, sir.
So do we really need to perform a full DFS?
I mean, at this point, it doesn't matter, right? Because at this point, one full DFS is just another linear thing. See, n different linear things is not good, because that is n times linear, which is quadratic. But just one additive linear thing is not harming you, at least not in the asymptotic sense.
Sir, also, so how do I know that I wouldn't accidentally perform this procedure n different times?
You will procedure in different times, possibly.
So in that case,
So that's what I said. So every time you're doing a time, I'm not saying the time complexity is E plus V. I did not say that.
that's why RU is required. Okay.
Yes, that's why I'm using RU and E of RU. Okay. E RU is smaller than N, E of RU is smaller than M. But it is significantly smaller than N and M. Okay. I mean, think a bit. I mean, everything that it is. Are you guys all fine? Or should you guys want to? Okay, why don't I? So let me leave here for now for this particular problem. You guys, of course, feel free to talk to your friends and discuss. Okay. If you have any doubts, let me know. It's not like this is the kind of a central problem or such a thing, but this kind of shows you how it can be done. And note that I'm not using any non-trivial ideas, right? I'm not using any non-trivial ideas. It is just DFS done one by one. And the only issue is that I've done is that few things like at the end of the day proving that there is no mother vertex in RU or RV and so on and so forth. Those are all simple. Possibly the only non-trivial thing is that I am time complexity analysis. Okay. The time complexity analysis is not every time I do it, I'm not saying, oh, it is linear. But linear, it is linear, but linear in what? Okay, so in some sense, let me say it in this way. You can write it for that matter. If I can find a different color, it will be helpful. Say after doing all of these things, you have N. N is the total set of vertices, right? And you have M, the total set of edges. Now you are splitting up this set of vertices and edges into some ways. Okay, what are you doing? You have N1, N2, N3, N4. Note that this is a partition of the vertices that has happened. right? Of this n1, n2, n3, n4, no problem. And what is m1? M1 is the set of edges induced by n1. What is m2? M2 is the set of edges induced by m2 union n1 minus the set of m1. Right? So meaning this is basically m2 is a set of edges which are here, here, and here, but not the edges within the first partition. Similarly, n2 and m3, n3 and m3 is set of edges that are, edges within itself, within from this set to other set, and that's it. So note that this is a partition, and the crucial part is the first DFS takes order n1 plus m1. Second DFS takes order n2 plus m2. Third DFS takes order n3 plus m3. And when you add it up, it is no longer n times n, right? N times the number of times you are multiplying it. But it is just order of summation of ni's, which is exactly, this is n1 plus m1, n2 plus n3 plus n4, right? M1 plus so the ith DFS takes order mi plus order ni. So this is the only clever or slightly involved time complexity analysis that has been done. Fine, is it clear?
Yes, sir.
Okay. Any doubts? Okay. So if you don't have any doubts now, let me jump into our today's topic, and this is kind of a very beautiful topic, and it will completely, yeah.
Sir.
Yeah, go ahead.
Sir, I have a doubt, but not about this. Not about this, sir. Sir, if I want to search a number from in an array, then we can do it in linear time. And if we want to find a string, I mean, the array is given as the array of characters, array of strings, and if we want to find some string, whether it is in that array or not, then will it take order of n time, where n is the number of strings in the array?
No.
I mean, we have to compare with each of the.
You have to do I think you have to do a dynamic programming, which will take order of the number of elements times the size of the string that you are looking for.
Okay, that thing I.
Yeah, I don't think there is a linear time server.
Okay.
Okay.
But sir, won't that be linear in the size of the inputs?
No, it is not, right? Because it is, I mean, it depends on what is the input, right? So if I give you an array of size n, and the string that you're looking for is a size square root n, right? So the input is basically an array of size n and the input of size square root n. So the input size is n plus square root n, right? But the time complexity of, because of the dynamic programming, will be n times square root n, which is n to the power 3 by 2. Right? N to the power 3 by 2 is not, right? So input size will be n plus square root n, right? N is the array, and square root n is the string that we are looking at. Okay, and the DP computation, this will take n times square root n, right? Because you have to create this array, this whole matrix and all. I mean, as far as I can see it in this basic thing.
So, but the input is n strings, right?
Oh, okay. What is okay, now I'm completely lost.
Yes, sir. I was saying that array in the array each element is a string, and we are searching a given string whether it is in that array or not. I mean,
Okay.
say
Yeah, so then all you're saying that you will need n comparisons, and all you need to do is comparisons, right?
yeah. I mean, can we take the comparison between two string?
In order one steps?
Yes, sir.
No, no, yeah, you can, but again, in that case, what your friend is saying is correct. The input size is therefore n times, it will be linear in the input size. So you have an array, right? You have an array of length n, when each array is a string of length something, so sigma to the power k, right? So the input size in that case, what is the input size? This is n times k, right? Because each of the elements is k of them, right? K bits
Sir,
things.
what is sigma?
Whatever 0, 1, alphabet, whatever the sigma is the alphabet. You have an alphabet, right? Strings on what? 0, 1 string, ABCD string, what is that?
ABCD string. Sir.
Yes, so this is the English alphabet.
Okay.
Okay. You're still, are you confused about sigma to the power k?
No, actually, you are saying that k is the maximum length. It can be right.
Okay, k1, k2, till
Okay,
kn.
okay, okay. Okay, okay, sir. I understand.
Okay, so then it will be summation of ki's. Okay, and I think you can do it in summation of ki steps, because when you coming to a particular string, right? Okay, I give you a string A and a string B. This has size k1. This has size something, I don't know what is that. Okay, question is that is A and B equals, how much time will it take to check if whether A and B is equal? How much time can it take? How many steps it can take? Of course, less than k1, right?
Yes.
So you will go for it linear scan and you go on checking that. So the input size will be, so the time complexity will be just like you order n, right? Order n was because it was order 1 query for per element of the array. Now you have, when you have come to the ith place to check it, it will cost you k1, ki. The total time complexity will be summation of ki, which is exactly same as the
And if my size is same, then we have to compare the whole string element wise.
I don't understand it.
Actually, I want to
Do you have a
see
problem in mind, or you are just giving something? You do
No,
have a
sir.
problem?
Actually, I am saying this because in problem set 3, question number 5,
Yeah.
they want to give an algorithm in order nkm time complexity, and so that's why I am asking to compare the string how many times we required.
See, if you are given two strings of size k1 and k2, okay, the time taken to compare these two strings takes usually minimum of k1 and k2.
Okay, sir.
Okay, but I don't know whether this is exactly the question that is there, or I'm understanding it correctly.
Okay, sir. I understood the thing. Then I will try.
Okay. Okay, so any questions? Okay, so let me really jump into this, whatever we are going to do today, because this is something very, very, very essential, useful, and I have heard that you guys have done something in class in the last course, but something that is not yet clearly told to you. So let me start with a very simple thing, okay? Say you are a librarian, okay? And, okay, so you have a set of books and you have a set of visitors. Okay, so these are the books and these are the set of, readers. Now, reader 1 is saying that I want one of any of these 5 books, and then uses 4 books. Reader 2 says that I want this and this book, one of them, not both of them, just one of them is good enough. Reader 3 says that I want this book, right? Reader 4 says that I want this book and this book. And reader 5 says that I want just this book or this book. Okay. So I have these readers R1, R2, R3, R4, R5. And here you have books B1, B2, B1, say B2, B3, B4, B5, B6, B7, B8. And your job is to assign the books to the readers such that, what would you like to have? So these are the people who want to read books in the inside library. What do you want to do? You want to ensure that as many number of people can read, right? So every person should be given at least one book, or not exactly one book, and everybody should be able to read. Correct? So you apply a greedy algorithm, say. Hello, okay, good. So B1, oh, reader 1, you want, so this is not a good one. So, yeah. So say, oh, reader 1, you want B1? Okay, very good. I am going to assign you B1. Reader 2, what do you want? Oh, you want B1 and B2, B3. Sorry, B1 is taken. I will assign B3 to B4. B3 to you. Reader 3, what do you want? Oh, you just want one of them. Okay, yeah, B6 is available. You take it. B4, you said, okay, what is there? And now you see there's a problem. B4 says, oh, okay, you are done. You are asking for B1 and B6. You don't have it. Get lost. You cannot assign you anything. Similarly, reader 5 comes up and says, oh, I want B1 and B6. No, nothing can be done. Do you think this is an optimal thing that has happened?
No.
No. Why not?
The reader 1 can get B7, and so like one more reader can get a book.
So you're saying that maybe if I don't give B1 the book, right? Instead, you are telling me that, oh, let me give B7 to reader 1, and then B1 is empty, then I can give B1 this book. And that is good. So I can achieve one more extra thing. Okay. So this process is basically what is called a optimization, and this is an optimization on a combinatorial object. Okay. So what is the object that we are looking at? So we are looking at what is called matching. What is the matching? So matching is if you get given a graph, okay, V comma E, So matching is a collection of edges. Okay, U1, V1, maybe U2, V2. Okay, it's a U2, V2 till UK, VK. All of them, these are a subset of the match edges. Okay, these are the edges that I have colored in red in some sense. And what is it required to have? What is this property that it is supposed to have? Property is that these elements, these vertices that you have found out, right? That the set. So okay. So for all I and j, ui should not be, so for all I and j, I not equal to j, of course, ui is not equals to vj. Oh, sorry, I mean ui is not equal to vj, and ui is not equal to vi also. In other words, no vertex should be present twice. Okay, every vertex should have one presence only. Say for example here, the main idea is that, so there's a lot of ways of explaining this whole thing. One of them is that you can say that, oh, see, I mean, this is the edge. So matching is this, and this. These are the matching, right? So the edges are B1 R5, B3 R2, B6 R3, and B7 R4, R1. These matchings are disjoint, right? Fine. Another way of saying it, same way, is that for all vertices in the graph G, there exists at most one. So, and by the way, these are called the matching edges. Okay, these are called the matching edges. M1, M2 till MK. There's at most one matching edge which contains V. So no vertex should participate in more than one edges. Okay. Now, this is something that so the matching is a very, very, very important thing particularly in, I mean, computer science, of course, but also in applications. Unbelievable thing. Okay. So for example, you have kidney donors and kidney recipients. Who would get what? Okay. Of course, not everybody's kidney is susceptible to perfect for the other person. Or job allocation, right? Maybe so in a company there are 20 jobs that has to be done, and you have 20 people, right? But not everybody can do all jobs. Maybe some people can do certain kind of jobs, and the other people can do other kind of jobs, and so on. You want to ensure that maximum amount of jobs are being solved at one go, right? So in some sense, you want to ensure the maximum matching that can be there. But if you do it wrongly, it might be that it is not optimal, meaning some person is kind of left without a job, although a proper allocation would have given that person a job. So this matching is like a very, very important concept that can be there. Another thing that can happen is that happens a lot is this is something that happens in the international level quite a lot. Say you have these countries, right? You have the, say, oil producing countries, and you have the oil receiving countries. So they are the people who want, these are the oil exporters, oil exporting countries, and these are the oil importing countries. Now everybody, what all things we have? Each oil importing country is saying that, oh, I want, say, 4, whatever that quantity is, say, 4 million gallons of oil or something like that. Okay. So 4 ships of oil. Okay, something like that. The other person is say, oh, I want only 2 ships of oil. Otherwise, oh, I need 10 ships of oil, and so on. And the oil exporter says, see, this time I have produced 5 ships of oil. The another country is saying, oh, I have produced only 1 ship of oil, and so on and so forth. But there's the problem. Not everybody can export to everybody, right? Say at this point, say USA and say India has a fight with some country and say, oh, I will not. This edges possibly represent the relationship with the countries. Meaning, this means that this country is ready to take oil from any of those countries. But here is a country from which this country don't want to take oil. I don't want to have any interaction with that person. And you can, I don't know whether you follow the politics and all. It keeps on happening all the time, right? US has a fight with Iran. This person has this one, and maybe so there is a kind of trade agreement that is there. Various countries have various rules and all those kind of stuff, and you have a set of oil exporters, set of oil importers, and a particular restriction of where the oil can go and where the oil cannot go. Now the job, of course, of a person is to kind of come and see that, oh, see, I want maximum amount of oil to go from one country, to be kind of going from the exporting country to the importing country. How will you solve it? What is the optimal solution? What do I mean optimal solution? What is optimization here? Optimal is that try to channel maximum amount of oil from exporting country to importing country. Now see, I mean, if you are only concerned about the world as a whole or something like that, you don't care about whether a particular country gets the maximum or not. But the main idea is that there is this much demand overall in the world, there is this much supply overall in the world. I want to match it as much as I can. Okay, how do you solve it? Is the problem clear? Hello?
Yes, sir.
Problem is clear, right? Okay. So this is slightly different from matching. Why? Because this country is saying that I want to take oil from this country, but this country just wants 4 ships of oil, nothing more. So even if this country wants to send 5 ships of oil, this country is not willing to take it. Okay, this country just takes 5 ships of oil and that's it. Yeah. Or maybe this country says, I want 10 ships of oil. And possibly there's no country in the world that can supply its 10 ships of oil in one go. So it will be happy to say that, oh, give me 1 ship of oil from you and 8 ships of oil from here, and so on and so forth. Similarly, of course, the exporting country might end up splitting up its oils in various parts. It says, oh, good. I mean, why not I send 4 ships of oil here and one ship of oil here? From the point of view of the exponent, it doesn't matter where it is sending. It wants to clear up its oil resources, and this set of people just want oil. From wherever it comes, it doesn't matter, as long as they don't violate any bilateral agreement. So do you have any idea about how this can be sorted?
So it's like a network flow problem with matchings.
It is like a network flow problems. Now, of course, I was going towards that. Okay. But I don't know how many of you remember that network flow problem. Okay. So let me explain you what a network flow problem and then come back to here. Okay. I will come back to here. So what is a network flow problem? The network flow problem, you have a start state, you have a finishing state, a start and a finish. And here there is a lot of edges that are a lot of vertices, they are nodes. Okay. And there are edges, some edges between this set of vertices or okay, something like this. Now, each of them also contains a certain amount of capacity. Okay. So this, let me give some numbers here: 4, 5, 6, 1, 6, 8, 2, 9, 3, 1, 2, 5, 6, 4, 7, 9, something like that. This is the capacity. And think of it this way, that these are the pipelines. Okay, this is the pipelines that are there. Meaning this pipeline here, so this is the water. Say think of it as a water, or so this is the water is being pushed into it, and water will come out of it. Okay, so you want to send water from S to T, but there is no direct pipe from S to T. There are there's a network of pipes that goes through various stations. Okay, and between stations you have pipes, but that is not unlimited amount of water. Which says, oh, this pipe on one day can only allow 4 units of water. This pipe can only have the capacity of sending 5 units of water. This one has capacity of sending 1 unit of water, and so on and so forth. Okay, so maybe I will just yeah, whatever. Okay. Now your job is to pass water. Okay, you have to create a flow. What is the question is that what is the maximum amount of water that can be sent from S to T? Okay, by the way, note that I have not even talked about any algorithm. Okay, this is, I'm still working on a very discrete math level thing. Okay, it's just pure mathematics kind of stuff. We'll come to that algorithms part possibly next week, in the next class. So, okay, good. So you said, oh, very good, excellent. So why don't I push 4 units of water here? Okay, let's see, let me use a different color. Let's be here, I have a big chunk, I send 4 units of water. And I have 5 units of water, I send it. What's the big deal in that? Now this 4 units of water goes here. Okay, you have 6 unit capacity, but see this node doesn't have any extra source. The source is only starting here, right? And neither does this any of them. Any of these nodes are kind of just a just a middle node. So they don't have any place to store the water. They are not receivers. It's only one source and one receiver. That's it. So you have 4 units of water and you have a 6 unit capacity, right? You cannot produce extra 2 units of water. So you have to pass only these 4 units of water. And at this point here, here's the 5 unit of water. Perfect. I have 1 unit of water here. Why don't I split up and send 1 unit of water through here and the 4 units of water through here? Now at this point, what happens? It is getting 5 units of water, but it has only amount for sending 2 units of water. So I cannot hope to send more than 2 units of water here. So what happens to the other 3 units of water? Okay, it cannot be stored here. So my initial algorithm was already wrong, or initial way of pushing things. Okay. So what is it that we want? So let me just try to formally write it up for something. So what do you have? You have this graph, which is a V comma E. Okay. And you have a capacity on each edges, which is, say, I am taking it from edge set to the reals. And what do you want? So we want to find a flow. This is a flow. What is a flow? Now let's see. A flow is nothing but a kind of a mapping from the edge set to the real numbers. Okay. This basically says that how much flow am I going to pass from U to V when there is an edge from U to V. But it should satisfy some properties. What are properties should you satisfy? What do you guys think? Can you suggest some properties? Hello.
Incoming flow should be same as outgoing flow from in every node.
Oh, very good. So for every node vertex in the V, the total amount of things that are coming in, which is summation of f of uv, right? Sum over u. This is the amount of flow that is coming in. This is equal to the amount of flow that are going out, v comma u, where sum over u. So because there is no storage at that point. So this is what is sometimes called the Kirchhoff's law. Okay, something that you might have seen in your 12 in physics. And there's one more property. I mean, that's kind of maybe so obvious that you guys are not saying it.
Flow can't be higher than capacity.
Yeah, flow cannot be greater than capacity. F of E must be lesser than or equal to the capacity of HE. And this is a flow, okay? Any flow of this kind, oh, sorry, now I have to be a bit careful here. This is for all V. There's only 2 vertices which doesn't follow this Kirchhoff's thing. Which are those? It is this one and this one. S can have unlimited amount of supply, and T can have unlimited amount of things going out. So this is for all V of V minus S comma T. This is the case. Okay. And if you satisfy this thing, the amount of water that is flowing from S to T is what? The size of the flow is the total amount of water that is being pushed in from S, right? So it's summation of f of S comma U over U. But yeah, I am saying S comma U and all, I mean, these are all edges, okay? These are basically edges, not paths. I really mean edges. Okay, because flow is defined on edges. Okay, and if there is no edge, then it is 0. Okay, if such no edge is there, then the flow is 0. The size of the flow is this. So goal is to find the or a maximum flow. Sometimes it's called the ST flow because it's sending from S to T. Okay? And this is the problem. Given a network, I want to find the maximum ST flow. Okay? Is this problem clear?
Yes.
Yeah, somebody wanted something else? So although this problem might look like a toyish problem, but this is not. This is a very important problem. So let me go back here and try to understand what's going on. How can I convert this oil export problem into this setting? What do you do? Can you help me do something like that?
We can create a source node and attach all the supply, create several nodes of several edges of infinite capacity to all the suppliers. And
Really?
similarly for this thing,
Really? Okay, good. So let's see. Okay, so you have a source node, and you're saying that, oh, this is what I'm doing. I'm going edges to all of them. Okay, and your goal. See, as a person who is working in the world good or world bad, whatever, solving, using more oil is not very good for the health of the earth. But anyways, but if I want to just maximize the world's oil flow from export country to output country, I am more interested in, it's like S and T are artificially put some sets, okay, from which I'm trying to sell it. It's like, oh, S is basically say the earth is can produce enough amount of oil and is going through the export companies to the import companies to T. Excellent. But what are the capacities?
we can take the capacity as the minimum of the capacity of the two end nodes.
What do you
Like
mean
for the
capacity of nodes? What do you mean two end nodes? Which end nodes?
Suppose we take the topmost edge, the one connecting 5 ships to the 4 ships,
right?
And we take the capacity as the minimum of the capacity of the end vertices.
Okay. So your friend is giving a suggestion that why don't I put capacity of each edge here as the minimum of the capacity of these two things. Meaning, if this person is willing to send 5 ships and this person is willing to take 4 ships, then capacity of this edge is 4, and so on and so forth. Okay, and he says that all of this capacity is put to be infinity, and then the maximum oil that can be transported from S to T is the maximum flow from S to T.
That's wrong.
That is not right, and I let you go and think about it. Okay, why is it not right? Why will it not give you the desired result? Okay. Instead, what you can do is that here you can put each node here has a capacity. So this capacity is like, oh, this much is, so this exporting company can only get 5 ships. This export company can only get 1 ship, and so on and so forth. And here also it says, oh, if you are sending, so like you can think of this one to be, I mean, if I want to be a bit dark, so this is the belly of the earth from where oil is coming out, and this is the gas emissions. Okay, and all I want is to ensure that maximum amount of oil is going out of the belly of the earth and coming out of the gas emission. Okay, so here this node, this is basically saying that this country can produce or can basically supply or whatever at most 5 units from the belly of the earth. And if I put here, like, okay, maximum amount of gas emission that you can have through this country is 4. So I just put these capacities over here. Okay. And now I put infinite capacity here in each of the edges. Okay, good. Now that's it. I mean, each notion, from each ship, each country, you have this much amount of supply, and each importing country, you can at most waste this much amount of bond, this much amount of oil. Now find the maximum flow. The maximum flow is exactly equal to the maximum. I mean, I didn't prove it, but prove it to yourself. Is the maximum amount of things that you can send from S to T. Sorry, the maximum amount of flow that you can send from S to T is the maximum amount of oil export that you can have. So this is just one example of how powerful is this notion of flows. Okay, this is not the most powerful form of it. Okay, we will, so now we are in the last 3 weeks of your classes, and we will basically now go from very specific small problems to general problems. So this is possibly the first major general problem that you can think of. Many problems can be solved or put up in this framework and solved. Okay. Instead of reinventing the wheel, in most places of the industry and all, what people do is that if you have to solve the optimization problem, you cast it as a flow problem. And you can see there's a very natural casting of the flow problem that can happen. And you can be very creative with this kind of creation of this graph and the flows and all. And then solving the flow problem will solve you the problem. So this is the flow. And so the question now that comes out is that, so I hope that I have kind of motivated you the problem to some level. Okay. So the question is that how to find, we have few questions, how to find the maximum flow in any general graph network. Okay, so there is this thing that I was told that you guys had done in your last discrete math course, which is called the Ford-Fulkerson method. I will possibly go over it to some level next class. Okay, that will show you that there exists an algorithm to find it. That's all. That algorithm will not be efficient. Okay. Second question would be a natural question is how to make the algorithm efficient. And the third question, which is even more interesting from people from your way, is that what are the properties of max flow? Okay, and then you will see this. It has very strong properties in lot of things. So it's called the max flow mean cut theorem and all those things. Okay, and these are the 3 questions that we will be studying for the rest of this week, and possibly a bit more after that. Okay, and in the next week we will generalize this particular setting to the next higher setting. Okay, so flows, the structure is a very general problem. Okay, and how to solve it. So you have to learn few things in flows, how to model various optimization problem in flows. So we will give you a set of problem sets this week, which will have all of them. By the way, a set of assignment will also be on your way. It should be coming out today or tomorrow, something like that. Then you have to learn how to solve the flows and these algorithms and all. We will, okay, and what are the various properties that are there. So this part is in some sense a bit more discrete mathish. So is this one. Okay, Both of them are discrete math kind of stuff, and this is a bit more algorithmic structure that is there. And then in the next class, we'll see the next higher level. So I will stop soon. So now I ask really for you guys to please during the last 3 weeks of this course, please read some stuff. So chapter 7, 7.1, 7.2, and 7.3. If you can read these 3 things, it will be outstanding. Okay. I mean, not outstanding, you have to read it. 7.1, 7.2, 7.3. Firstly, because anyways, these are something that you should have done in discrete math course, and it just supposedly has been done to some level, maybe online, but not in a physical class. But anyways, so 7.1, 7.2, and 7.3, please read and come on Thursday. Okay. And in the meantime, let me just ask you one question, just if you can, one of you can answer. Have you heard some problem, some course on optimization till now?
We had a little bit of optimization numerical analysis.
In numerical analysis, okay. And have you seen things like linear programming? You know what is linear programming?
At least I did linear programming in 12th class.
Oh wow. What about the, forget 12th class. In ISI, whatever. ISI it was not done, right?
No.
Okay, good. Anyway, this was, let's forget whatever I asked in this setting. I mean, this is not what is the main. I mean, I will come to this next week. So let me stop here. So we have this graph networks, a kind of toyish problem, which is very general, actually speaking. So these are the set of problems that are there, and in section 7, and also in some of the questions that we will put in front for the problem set, you will find how to model various optimization questions. So what is optimization question? In short, optimization is nothing but find the maximum of something under certain constraint. What is the maximum flow that you can have when the flows have this structure? Okay, so this kind of stuff. Or what is the maximum oil export that you can happen when everybody has various constraints like this. So these are basically what is meant as optimization problem. Optimize something under constraints. Okay. I mean, you have seen optimization, what is optimization is in numerical analysis. So hopefully you are familiar with some amount of high level concept of optimization. But many optimization problems can be modeled in the language of flows. And this is what you should study, read, and get used to. So we'll meet on Thursday, and you are really requested to read 7.1, 7.2 as well. Okay. I mean, I can take some questions, but we can leave also. Any questions?
Sir, how many more assignments will you be giving?
How many marks? What?
How many more assignments?
I think 2 more maybe. So this week there'll be 1 and possibly 1.
Like I think we had something like 5 out of 7 or something like that, right?
Yeah, I don't think we can hit 7. So maybe it will be 5 out of 6 or maybe 4 out of 6, something like that.
Okay, sir.
Yeah, I don't think we'll hit 7 assignments. Yeah. Okay. Fine. So okay, let's stop then now.